So go ahead, load up this page. No cheating. If you want to work in Notability, go ahead and do the answers right on the screen. If you don't have Notability, go ahead and do this on paper. But there are 9 questions here, 9 different situations. In the following scenarios, indicate the change in potential energy of the particle. Scenario 1, you have an electron moving from an initial position to a final position. What is the change in potential energy? Situation 2, you have a proton. Situation 3, you have a neutral hydrogen atom. Situation 4, you have an electron, etc. Go ahead, do those now. Feel free to consult with the people sitting next to you, see what they get, see if you agree. Go to work. You got about 5 minutes to do this. Take a look. What do you think?
Oh, it is 0. Huh?
So, 1, 3, 5 are all no change. Why is 1 no change?
Same distance from the...
Yeah. Ends up to the same distance, so same voltage line, right? If you're on the same voltage line and you've got a charge moving from 6 volts to 6 volts, what's the change in voltage?
0.
Nothing. And so no change in potential energy. 3, why is 3 no change in potential energy? That's right, it's a neutral. Neutrals mean there is a change in voltage, however, the change in potential energy must be 0 because potential energy is the voltage times the charge and there's no charge. Number 5, why is the change in potential energy 0?
5.
Because
It's
it's
still
like
just
they can't
paralyzed.
travel on that line.
I don't care about field. Don't tell me about field. What are we talking about now?
Because there's a positive and negative on each side. No, there's a positive.
Tell me about voltage.
It's 0 on the line.
Yeah, there is an equipotential line that runs the locus of all points equidistant from those 2 charges. In other words, there's an equipotential line running vertically halfway between those 2 charges. So as long as you start on that line and end on that line, you're at the same voltage. And if you're at the same voltage, same charge, that means same potential energy.
What is that line? It's like...
Why does it exist?
Yeah.
Okay, who had this particular plot in class? A positive charge, a positive mountain, and a negative sinkhole. All right, and you also had it on your quiz. You remember it?
Yes.
You remember that there was an equipotential line halfway down the middle? Yeah, that one. Yeah. So anyway, so yeah, it's 0 volt equipotential line, assuming the charges are equal. Number 7. Why is the change 0?
It's about the same line.
Same equipotential line. All right, fine. Number 2. Why did that proton lose potential energy?
Further away from the positive.
It came further away from the positive charge, or if you talk about voltage, move to a lower voltage. Good. The electron in number 4, why did it gain potential energy?
Move farther away from the 2 positive charges, so it's more attracted to the so that makes the voltage.
All right, so the voltage actually decreases.
Oh yeah, I meant...
The voltage that it's at decreases in 4, right? It goes from a higher voltage to a lower voltage. But it's a negative charge. So negative times negative makes a positive gain. All right. What about number 8 and number 9? Why are they both the same?
Field lines point away from positive charges. So
No, field lines don't. Field lines point down the voltage hill.
So as it travels further along the field lines, the voltage went down.
Yeah, so the down is indicating the direction of decreasing voltage.
You have someone at the door.
Got it.
Signature.
All right, so answers on the next page. If a positively charged particle Q were shot towards big Q, would it speed up or slow down? Now for this one, I want you to work together in your tables and come up with an answer. Would this positive charge speed up or slow down as it was approaching big Q? And I want you to explain your answer based on force, based on electric field, and based on energy. So you should have 3 different explanations for this. You've got 5 minutes. Go. Okay, so we know it's going to slow down, but who's got a good explanation using like forces between 2 charges? Yeah, go.
Because the forces are repelling each other, right? Because it's positive and positive. And then as it gets closer, it like gets even stronger repelling, so it accelerates.
Would it slow down even if it didn't get stronger when closer?
Yeah.
Okay. But stronger when closer, how does that affect its slowing?
Parabolic.
It goes like.
It makes the acceleration even greater. Okay, good. Who's got a good electric field explanation? Yes, go.
Electric field is running from like away from Q, and since Q is like or small Q is positive, it's going against the direction of the field, so it goes down. If it's negative behind it, or anything against it, it's positive.
All right, perfect. I love it. And I love that you mentioned what a negative would do as well, right? Big Q creates the field radiates outward, and if you've got a little q sitting in a field going to the right and a field pointing to the left, it's got to slow down. And a negative would do the opposite. Yes.
Oh, I was gonna give an
Energy? Yeah. Oh, go ahead.
Would like the field from if little q was like big enough to charge, would the field from it like?
Very interesting question. This idea of a test charge. If your test charge little q had a big enough charge such that it's kind of creating its own field that's not insignificant, would it affect the motion of little q? Let me say that again. If little q's field mattered, would little q push on little q?
An object can't push on itself.
Exactly. That's a violation of Newton's third law, right? You guys remember this? Take out your hand, stick it on your right side, try to push yourself across the room. Go. Right? Can little q create a field that pushes on itself?
No.
No. That's impossible.
Wouldn't move like big Q.
Does little q create a field that pushes on big Q? Absolutely. Right? So yeah, a charge can't create a field to push itself. That doesn't make any sense. All right? So the field that matters is all the field that was created by every other charge.
She says hi, Mr. Basement.
Okay, good.
Who were you talking to?
I have no idea. All right. Next, moving on.
He says hi.
All right, so potential energy. You guys should be familiar with the idea of potential energy. If you have, we talked about this for masses. If you have 2 masses, when is the potential energy between them going to be 0? At infinity, if they're infinitely far apart. And as these masses come closer and closer together, what happens to their potential energy? It decreases. Right? It becomes, if it starts at 0 and gets less, it's getting more negative. What if you had two positive charges?
Now it comes to charges.
If you start at 0 and you bring them together, it takes more and more energy to bring them together. That means their potential energy is increasing with two positives. All right? You get them infinite, or you get them right next to each other. That means the energy's got to be really, really big. Okay, so derivation of that. We're going to start with F equals KQ over X squared. The work it takes to go from infinity to 0 is negative integral from infinity to d of f dx, which is the same as the integral from d to infinity of KQQ over X squared. I got rid of the negative sign. Integrate, plug in some stuff, and you end up with the potential energy between two positive charges is KQQ over d, which should look familiar from yesterday. All right, so that's two positive charges. What if one of the charges was negative? Well, they would attract, right? And if you have two attractive things and they are getting closer and closer together, that means they're losing energy. Or the other way of thinking about that is two attractive things, if you want them to gain energy, you have to pull them farther and farther apart. All right, so closer and closer together. That means it's the negative of two positives. So the energy would be negative KQQ over D. All right, moving on. Okay, example problem. You have a little piece of plastic, 2 millimeters in diameter, and it's got a negative charge. If you were to shoot a proton at it, when the proton hits the plastic, what speed is it going? All right, and before you start this, is the proton going to slow down or speed up?
Speed up.
Why is it going to speed up? Because it's attracted. What is the proton's initial potential energy?
0.
Why is it 0?
It's very far.
Very far away means potential energy is 0, right? And is the proton going to gain or lose potential energy? It's going to lose potential energy. Why? Because it's speeding up, gaining kinetic. All right, you've got 5 minutes, go. All right, so the rest of this is going to be a lot just like your homework packet, but the basic idea, you could solve this with an integral. If you wanted to integrate KQQ over X squared as the thing approached and use the work energy theorem and all that mumbo jumbo. But the easiest way to do this is with basic algebra. All right? Use the law of conservation of energy. You take the initial, what kind of energy does the proton start with?
Kinetic.
Kinetic. Why doesn't it start with any potential?
It's very far away.
Because it's very far away. When it's touching, when it finally hits, does it have any kinetic? Absolutely, because otherwise it wouldn't impact. Does it have any potential? Yes, it does. So the equation would be your initial kinetic equals your final kinetic plus your final potential. Yes?
I thought the potential was like -30.
Ah, good question.
So how do you plug that in?
Ha 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 ha. Here. Good question. Let's say I have a big charge and a little charge. They are touching each other. What is the distance between them?
R, the radius of the big charge.
That's annoying.
It is not 0. It's the radius of the big charge plus the radius of the little charge. If your little charge has 0 radius, then it's just the radius of the big charge. Got it? Now, you would be right if both charges had a radius of 0. The force would be infinity and everything would blow up and you couldn't do it. But the radius is not 0. All right? I will leave the rest of this as an exercise for your homework.
They didn't give you the minutes.